This now is the last video for Chapter 6. We'll be looking at frames and machines. The difference between frames and machines and trusses is that in these structures, some of the members have more than two forces being applied to them. So what we want to do is find the forces at the joints between the members by applying the equations of equilibrium. And once we have these forces, this allows an engineer to design the parts for the structure of a machine using strength of materials concepts. The steps are to first draw the free body diagram for each part and then identify all the two-force members, and be sure to show that the forces which are common to two parts are equal and opposite. So that is, a force acts in one direction on one part, and then the adjacent part, the force acts in the other direction. The figure here is a machine, and it's made up of three parts. We have linkage AB, then the lever arm ED, and finally we have the block D, which runs in a smooth channel. C is the can. This is a can crusher. So the first step, again, in order to find the forces acting on these three parts of the machine, the first step is to draw a free body diagram for each part, and then find all the two-force members. So linkage AB is a two-force member. The joint at A and the joint at B are smooth pins, and those are the only two, the reactions there are the only two forces acting on AB. So we know the force at A and the force at B are on the line that connects the 2 points A and B. Here's the free body diagram for the parts of this machine. We have the lever arm ED. Here's the external force. Here's the reaction at B, and here is the force at D. And so this is a pin joint, so it can have a horizontal and vertical component. B is a pin joint also, but we know that AB is a two-force member, so we know the direction of FAB. It's 75 degrees from the lever arm. And then object D runs in the channel, so we have this normal force from the walls, and then we have the pressure of the can pushing back against it. And then, so here's the same force dx and dy that acted on the lever arm. It's just that on the object at the end, those forces are acting in the opposite direction. So dx on the lever arm is shown pushing to the left, thus dx on the block is shown pushing to the right. And similarly, dy on the lever arm is the opposite sense as dy on the block. And you can see FAB on the linkage AB is going in the opposite direction of FAB on the lever arm. So those are the free body diagrams for all the parts of this mechanism. And be sure to draw the forces being equal and opposite whenever they're common to two parts. Here's another example. This is a frame made up of two links, AB and BC, and if we want to find the forces in these members, we would follow the same procedure. So again, AB is a two-force member, so we know the direction of those forces, and then BC is shown with its reactions and the external 2,000 Newton force. Once we have these free body diagrams, we then apply the equations of equilibrium in order to solve for the unknowns. Each free body diagram provides three equations, and so for the number of parts, you can only have 3 times that number of parts of unknowns. So for this example, we have one unknown, FAB, CX, and CY. So that makes 3 unknowns. So we can solve for these unknowns without even using equations of equilibrium for link AB. In effect, we already used the equations of equilibrium, and they told us that FAB is acting in this direction. So we just took a shortcut by knowing that this is a two-force member. So doing that eliminated some of our unknowns. Okay, now on to an example problem where we'll solve. This is fundamental problem 613. And the statement is, determine the force P needed to hold the 60-pound weight in equilibrium. Well, this is really a simple problem. Because we're assuming that these are frictionless pulleys. So the tension everywhere in the rope is P. So we'll just draw the free body diagram of that largest wheel. So we've got 60 pounds from the weight, and then we have P acting up at the middle, P on the right, and P on the left. And so we just look at the force balance in the y direction. So you have 3 times P acting up, and then negative and 60 acting down. Gives us that the tension P is 20 pounds. Now on to a more challenging example, fundamental problem 16. Determine the horizontal and vertical components of reaction at pin C. We want to identify a two-force member if there are any. It looks like linkage AB is a two-force member because there are no external forces and it's connected by smooth pins. So we'll just draw the free body diagram for linkage BC. Here's FAB, just assuming that it's in compression, but we do know that it's acting at 45 degrees. We have an 800 Newton meter moment. .400 Newton applied force, and then the reactions at C. Drawn in the, assumed to be in the positive directions. We can find the unknown FB by taking the moments about C. So we have an 800 Newton meter force applied, and then the 400 Newton force has a moment arm of 2 meters. And then the Y component, the X component of FB let me rewrite this where I have more room to write. Sum of the moments about C is equal to 800 from the pure moment applied plus 400 times 2. Those are the external applied loads. Then we have the X component of FAB generates a positive moment, so plus FAB cosine of 45, and that moment arm is 1. and the y component of FAB generates a negative moment, so minus FAB sine of 45, and its moment arm is 3 meters, and all that equals 0. So we get that 1600 is equal to FB square root of 2, and thus FB is 1100 newtons. Now we'll do our force balance in the x and y directions. X component of FB gives us that FCX is equal to negative FB square root of 2 over 2, which is negative 800 pounds. I'm sorry, 800 newtons. So FCX acts in the opposite sense that we have shown in the free body diagram. Force balance in the y direction. We have the y component of FB, so that's FB sine 45. We have FCY, and then we have the 400 Newton applied load, and that all adds up to 0, which gives us that FB is square root of 2 times 400 minus Fy. That's not what we want. We want to solve for FCY. So FCY is equal to 400 minus FB square root of 2 over 2, which is negative 400. So we have that FCX acts left at 800 newtons, and FCY acts down with 400 newtons. So now an example where we actually have to use free body diagrams for all the different members in one of these machines. And that's problem 671. It's shown here. And we have these 3 beams that are connected by pin joints. The one on the left has a fixed support. The one in the middle has a roller support, and the one on the right has a roller support. We've got 3 applied loads, that is 2 forces and 1 moment. So again, identify 2 force members. There are none in this problem. Draw free body diagrams of all the members. So I'll just go from left to right. This has a fixed support on the left side, so you got AX, AY, 9 kilonewtons acting down. Oh, I'm sorry, the support can also provide a moment, so we'll go ahead and draw that positive direction, so we call it MA. And then the pin on the right provides reactions, BY and BX. So there's the free body diagram for the section AB, or the member AB, and I just assumed directions for the reactions at A and B. Now, member B, we've got the reactions at B, and so we already drew them in the certain sense on member A, so we've got to draw them in the opposite sense. I'm sorry, on member AB, so we've got to draw them in the opposite sense on member CD. So now we have BX acting to the left instead, and BY acting down, because the force on CD is equal and opposite to the force on AB. We've got this applied moment, and then the reactions at D. So there's the free body diagram for member CD. We've got the reactions at the pins at C and the pin at D, and then the applied moment. Now finally we just draw the last free body diagram. Member DE. We have a pin at D, so we need to draw the reaction forces from that pen, and the direction, these need to be equal and opposite to those on CD. So we have dx acting to the left and dy acting down. Got 10 kilonewtons down, and then the reaction at E, call it Fe. Oh, and I left off something, that reminds me, the support at C, that's pretty important, so Fc. I called it Fc. Yeah, this is really, remember, BD. C is the point in the middle, okay, where the support is. And so we want to start with one of these parts that has the fewest unknowns. And so that would be DE. There are 3 unknowns for that member, and so we can solve for those 3 unknowns using our equations of equilibrium for this rigid body, that is body DE. So we'll go ahead and start over here with the forces in the y direction. So we've got Fe acting up, minus 10 minus dy, and that sums to 0. You get Fe is 10 plus dy. Forces in the y direction is just negative dx, and that's equal to 0. And then we'll take the moments about point E. So we have 10 kilonewton force, 1.5 meter moment arm, and then dy also is a positive moment, and it has a 3 meter moment arm, and that sums to 0. So we get that dy is negative 5 kilonewtons. So dy on, remember, DE actually points up. So negative value means opposite to what we have drawn, so that force pushes up on member DE. And going back to this equation, we get that Fe is 5 kilonewtons. So 5 kilonewtons here, 5 kilonewtons there, balances out the 10 kilonewtons acting in the middle. Okay, so now we have dx and dy, so those are, now we can go back to this member BD, and these are no longer unknowns, so we just have these 3 unknowns, bx, by, and fc. And that will give us the support reaction at Fc. So we'll start with force balance in the y direction. We have Fc, dy. Okay, so this could get a little tricky. Dy is shown acting up, but we found it's shown acting up on BD, but we found that it acts up on DE, so it actually acts down on BD. So again, we can go ahead and just write a table with the final answers and then change our free body diagram. This is how we were doing with the method of sections earlier. So dy is 5 kilonewtons and Fe is 5 kilonewtons. And we'll change the direction of dy. So dy is shown up now here and down now here. So free body, the forces in the y direction on BD, we have Fc acting up, dy acting down, so that's 5 kilonewtons down, and minus by, and that all adds up to 0. So that gives us that Fc is equal to 5 plus by. We'll now take the sum of the moments about point C, and that leaves us with just one unknown, which is by. And we get 1.5 by is a moment, and then we have plus, well, dy acts down, so that's a negative moment. So So that would be minus 1.5 dy, and then we have minus 10 from the applied moment, and that all adds up to 0. And so we get that By is 11 2/3 kilonewtons. Sum of the forces in the x is equal to negative bx, and that's 0. So here we have, and then we can go ahead and substitute back for Fc, and we get that it's 16 2/3 kilonewtons. So this free body diagram is correct now that we changed dy. And we can go on to the leftmost rigid body. And now By and Bx are known, so we have these three unknowns, Ax, Ay, and the moment about A. Starting with force balance in the y direction, we have Ay plus By minus 9, and that equals 0. Oh, but By is 11 2/3. So that gives us that Ay is negative 2.6667 kilonewtons. So Ay is shown up, but actually goes down. Alright. And forces in the x equals Ax, Bx is 0, plus 0 is equal to 0, so Ax is 0. And the sum of the moments about point A, we have the reaction moment, we have the moment from the 9 kilonewton force, and we have the moment from By, and that all adds up to 0. So that gives us that moment of reaction moment A is 21.5 kilonewton meters. So we wanted to find the reactions at A, C, and E. So here they are. So Ax is 0, Ay is 2.67 kilonewtons down. Ma is 21.5 kilonewton meters. Fc is 16.7 kilonewtons, and Fe is 5 kilonewtons. So there's a fair amount of algebra involved with these because we have simultaneous equations to solve. And it's like 3 free body diagram or 3 rigid body equilibrium problems all rolled into one. So it can get a little bit long, but it's just straightforward things that we've seen before. So now one last example. This is fundamental problem 620, and it's the same steps again. The problem statement is to determine the components of reaction at D. So we want to find the reaction at D. And first we'll look for two force members. We see that there is a two force member. It's AB. AB is a rigid body with 2 pin joints and no loads at any other points, no forces at any points other than those joints, A and B. So we know so we don't have to draw the free body diagram for AB. So we'll just draw those for BC and CD. So here's BC. We've got FAB. We know its direction. It's a 3, 4, 5 triangle, the X and Y components. draw this bigger. Okay, so 3, 4, 5 is the direction of and the hypotenuse for FAB. And we also have two applied forces, 10 kilonewtons and 15 kilonewtons. And then we have the forces from the joint at C. So that's a pin joint, so it just gives an X and a Y force and no moment. And we'll go ahead and just draw those in the positive directions. So we'll call it CX acting to the right and CY acting up. And then we draw the free body diagram for the remaining member, and that's CD. So we'll start off with the forces at C and draw them in the opposite sense as it's shown for the free body diagram of BC. CX is shown to the left now, and CY is shown down. And then we have a fixed support at D, so that can possibly provide, or that's able to provide force in X, force in the Y, and a moment. So we've got dy, dx, and md. We're asked to solve for the reactions at D, but we can't do that just by looking at this free body diagram because we have 5 unknowns here and only 3 equations. So we need to go back to this free body diagram and solve for Cx and Cy. Here we have 3 unknowns, FAB, Cx, and Cy, and we can get those using our 3 equations of equilibrium. We'll start off with the moments about point C, because that will give us just one unknown. So that's 15 times 3, positive moment, and then another positive moment, 10 times 6. And then the y component of FB will provide a negative moment. So the y component is 4/5 of FAB, and then it has a moment arm of 9 meters. And all those add up to 0, and we get that FAB is 14.583 kilonewtons. And it is, in fact, in compression. So with that knowledge, we can solve for Cx and Cy. The forces in the x direction, we have 3/5 of 14.583 and Cx, and that equals 0. So Cx is negative 8.75. So it's drawn to the left, and it's actually to the right. We'll go ahead and put the final answers here. This isn't an answer, 8.75, but once we do this, then we can go ahead and change the drawing. So Cx acts to the left of 8.75, and we need to change this one too. Okay. Now forces in the y will give us Cy. We have the y component of FAB, 4/5 of 14.583, negative 10, negative 15, and Cy, and those all add up to 0. So we get that Cy is negative 13.3 repeating kilonewtons. So Cy acts down on member BC. So I went ahead and put that over here, and then now I'll change the free body diagrams. So it's down on BC, that means it's up on CD. Now we can apply the equations of equilibrium to member CD because Cx and Cy are known values. Start off with the moments about point D. So we get MD, and then only Cx generates a moment about point D. And it's a negative moment, so minus 8.75 times 4. Because we have Cx acting on D is to the right, and so it generates a negative moment about D, and it has a moment arm of 4 meters. So 8.75 times 4, and those add up to 0, so we get that MD is Okay. Forces in the x. So we have 8.75 plus dx equals 0. Dx is negative 8.75. And forces in the y equals 13.3 repeating plus dy, and that's equal to 0, so dy is negative 13.3. So dx actually points to the left, and dy actually points down. Well, I see looking back now that I made a mistake. Cy is going to be a positive value. We're going to have Cy is 25 minus 4/5 of 14.583. So that's positive 13.3. So Cy acting on BC actually does go up. That's okay. It's unfortunate that I made that mistake, but it does allow for a good teaching point, and that is when I solve for the reactions here at dy, I was looking because I found that it was negative, so that would mean that the ground was actually pulling dy down, or I'm sorry, was pulling point D down. That is, without this fixed support, remember CD would float up in the air, and then that didn't seem right because the applied forces that we have here are down. Sometimes things can be a little counterintuitive, but in this case I didn't see any way that the reaction at D should be holding D from going up. And so I looked back and saw that here was a mistake in my math, and Cy is actually positive. So Cy points up here, and that means that it points down here, like we had shown to begin with. So there's Cy points down. And so in this equation, we would have negative 13.3 plus dy, so that gives that dy is 13.3. So dy actually points up. Okay. So it's good, whenever you finish a problem, to just look at the answers and look at the schematic and check to make sure that your answers are sensible.